Okay, hello again. This is the video about chapter 6. This is the third one, and see how much we can cover in this one. I hope you're doing well, and so let us get started. So I'm going to start talking about a logarithm, and to do that, of course, we start working with some examples. So let's go to those examples here and get this wide area and work on this first, and then we come back. So what we want to do is this. So let me make this as big as possible. So what we want to do is something like this. We talked about exponential functions already. So I'm going to write this in red. So we know b to x, when b is greater than 1. In general, that graph looks like this, right? It goes to infinity this way and goes to 0 that way, and this is 1 here. So now the question, of course, we had another family. Let me also write it here, a b to x, where b was between 0 and 1. And the graph of those look like is decreasing, right, like that, and it goes up, right? So now let's do some scratch work here. If I take, let's say we have a function, right, and the input is 2, let's say, and so let's say 3, right? So the function is 2 to x, so the output would be, of course, f of x, and in terms of 3, the output for 3 would be, well, 8, because 2 to the third power is 8, right? Okay, now, what I like is a function that takes input and is the inverse of this function, right? And we already talked about logarithm, right? So the inverse of taking a number and raising to the third, taking a number and then using base 2 to exponentiate it, and we get 8. The inverse of this process is the logarithm. So it would be log base 2 of 8 and gives you 3 back. Gives you the 3 back. Now, in terms of formula, that would be log base 2 of x. So we can define the inverse of functions like this, right, as a logarithm function with the base b, the same base, and the same condition. B has to be greater than 1, right? So now we have what? We have logarithmic functions as inverses of what? Exponential functions. And the same is true for these, the family here. The inverse would be log base b of x, where b, the condition is the same, has to be between 0 and 1. The same condition applies, right? So these functions are called logarithm. So if you put 8 here, well, what is log base 2 of 8? That means 2 to what power is 8 is 3, right? So that's a logarithmic function. Of course, in this case, this is specifically the inverse of 2 to x. So if I want the inverse of 3 to x, I get log base 3 of x, right? Okay. Now, if we want to graph it. How do we graph it? Well, in algebra before in other chapters, we talked about the property of inverses, that what? That two inverses are reciprocal with respect to what? Not reciprocal, but symmetric with respect to y equals to x. So this 0, 1 here, the inverse of it would be 1, 0, because when you find an inverse, you're switching input and output. You see over here, 3, 8 becomes 8, 3, right? So 0, 1 becomes 1, 0, right? So 1, 0. Now, the horizontal asymptote for the red one is y equals to 0, right? So for the red one, the horizontal asymptote is y equals to 0. Now for the blue one, the horizontal asymptote doesn't exist. Why? Because y equals to 0 becomes x equals to 0, because we switch x and y. So that means it has a vertical asymptote at what? The blue one. At x equal to 0, right? All right. So that means this is the point, this is the vertical asymptote. So now, notice that this part that is approaching negative y-axis will approach negative x-axis. So it's going to be right here. And you see that these are reflections with respect to that line, right? And this part that is going up to infinity this way is going to go to infinity this way. So this blue graph is the graph of families of logarithmic functions with the base greater than 1, including the two celebrity members, log base e of x and log base 10 of x. Now, is the last time you see me writing these in this form, because you know the people who came up with conventions, they're going to get mad at us if we use this. But log base e has a notation, it's called ln. So instead of putting log base e, the famous number based on application of what? Exponential to, you know, compound interest, as continuous interest number. So it's a very famous number. It's on the calculator. So base e would be ln, natural logarithm. That's what this is a natural logarithm. And then base 10 is the same, except we don't write the 10. So if you don't see the 10, is a log base 10, and the name of this is common logarithm. Common logarithm, natural logarithm. Okay, so the graph of all of these will look like that blue one right here. Their sharpness is different, right? Now remember, these numbers, the bases are greater than 1. So the sharper this is, its inverse would be going to infinity is slower, right? The sharper this is, the slower this is going to go to infinity. So that means the logarithms that are kind of slowly go to infinity and they're closer to the x-axis here are the logarithms whose bases are bigger numbers. So if you want to compare log base 10 with log base e, log base 10 would be lower than log base e, because 10 to x is sharper than e to x. But we're going to see that when we graph them. But this is the graph. Now, what if the base is between, this is log, what if the base is between 0 and 1? Well, we do the same thing, but this time, again, we graph the y equals to x. So this point, again, goes to 1, 0. Now, notice that that point right there, see, that point right there, that it doesn't go anywhere because it's on this line y equals to x. So if you switch x and y for this point, the point doesn't go anywhere, so that means that point they have in common, the blue and the red. The inverse and the function have that in common. So this little part here, see that little part? Look at the rectangle control. So that's the little part right there. So that little part and has an inverse that has a reflection that is right here, right? And this part that is going to infinity this way is going to go to infinity, negative infinity this way. And this part that is approaching positive x-axis will be approaching positive y-axis. So that blue one is a reflection of the red one with respect to y equals to x. So the graphs of logarithm with base b between 0 and 1, including, you know, a bunch of them like log base 1/2 of x, log base, let's say 0.12 of x, and so forth. All of these kind of look like this blue one here. So it again is a decreasing function, the inverse, and the original function also is decreasing. Here the function is increasing, its inverse also is increasing, right? All right, now what about the domain and range of these graphs? Well, remember, another property of inverses is that when you switch x and y, you're switching domain and range. So we know the domain and range of the red one. So let's write it down. We know the domain of the red one in both cases, right? Let's write it in the middle here. So the domain of the red one is all real numbers, and the range is 0 to infinity. Now, for the logarithm function, the blue one, all we have to do, you can look at the graph and you can easily see the range and domain, but you could also look at this and switch them. So domain of the blue one is 0 to infinity, as is clear here. It's from 0 to infinity in both cases. And the range is all real numbers. So you can think of switching these two, or just look at the graph. See, the range is all real numbers here. Also, the range is all real numbers here. This thing is going to go, eventually is going to go to all real numbers, right? Okay, so that's how we graph logarithmic functions and exponential functions. Now, there is a connection between the two because of this idea of inverses. So if we have a, let's say I start with input of 2 to x, and I'll put a 3 here. Well, the f of x that comes out is going to be, of course, 8. Now, what if I take this and I put it in inverse function, which is what? Log base 2 of x. That's the inverse. This is the inverse of that. So what comes out is going to be, now remember this is f inverse, so it's going to be f inverse of f of x. And so what happens numerically? 3 goes in, 8 comes out, 8 comes in here, 3 comes out. So you input 3, you get 3 back. So if you input x, you get x back. So that means this is equals to x, right? So that is x. Now, what if you switch this order and you put log first here, let's say log base 2 of x. Let's pick a round number so we can easily see what it is. So if I pick log first and put 16 in here, then what do I get? Well, so over here, this is going to be f inverse, right? And 16, what's log base 2 of 16? 2 to what power is 16? Well, that's 4, right? Now, what's the inverse of this? 2 to, right? If you start with that, this is going to be the inverse, right? So this is the inverse of this, and this is the inverse of this. They're inverses of each other, right? So the output here would be f of f inverse, and numerically 4 goes in here, 2 to 4 is 16, of course. You get the same number back, right? Start with 16, you get 16. So that means this has to be x2. So there's an and here. So both of these have to be true if two functions are inverses. Now that gives us a way to actually speak in two different languages, in exponential language and in logarithmic language. So if I write 2 to the third equals to 8, logarithmically speaking, all I have to do to change everything in terms of logarithm is to take log of both sides with base 2. So that means if two functions are inverses, for example, let's say square root of x and x squared are inverses. So what happens if I have a square root of x, then I raise it to second power? Well, I get x, right? And if x is positive, and I take square root of x squared, I also get x, right? I say x is positive, right? So that means if two functions are inverses, they cancel each other, right? Notice the square root cancels x squared, you get x back. And then a squaring cancels the square root and you get x back. This is true for any two inverses, right? So it's true also for these two. So that means if I take this and substitute it in here, I'm going to get log base 2 and then 2 to x. Well, this structure here cancel that one. So log base 2 cancels 2. So that means you start with x, you do this to it, then you do this to it. Well, they cancel each other, you get x back, right? The same is true if you take this one and substitute it for x here. That means you take 2 to the power of log base 2 of x. And notice that, again, you start with x. What do you do to it first? This. And then what? This. Well, they cancel each other. So you get x back, right? So if I want to cancel this exponentiation, I can take what? I can take log base 2 of this side and take log base 2 of this side. Now, of course, now this log cancels this exponentiation, so we just get 3 here equals to log base 2 of 8. So you see this right here and this say exactly the same thing, but in different forms, right? This one says hello, this one says hola, which mean the same thing, right? But in different ways. So this is called exponential, and this is logarithmic. Exponential, logarithmic. Now we could also start with what? Logarithmic and convert it to exponential. And how do we do that? Well, we can do that using, I don't know why I can't. See there? Okay. So let's do that. So what if you have something like log base 2 of 16 equals to 4, right? So I can convert that to exponential. How? Well, I have to exponentiate both sides with base 2. So I have to take 2 and raise it to the power of the left side, and then take 2 and raise it to the power of the right side. Now I know what happens here. If you start with 16 and do this to it, then do this, since the bases are the same, they cancel each other. So on the left I get 16, and on the right I get 2 to the 4th. So this statement and this statement are basically the same. This says hi, that says hola, or the other way around, right? So this is pretty useful in solving logarithmic and exponential equations. Okay, we're going to use this idea. So let's do some examples here now. So we're going to do, let's say, number, it says to okay, for the following, rewrite in exponential form. So let's do a few of these. Actually, let's do 6 to, here we go. So I'm going to do all of these 6 to 9 quickly. So this one, what's the base? The base is 4, right? So what we have to do, we have to start with log base 4 of q, and we have to take 4 and raise it to the left side and raise it to the right side. Now, since these bases are the same, these cancel each other, so we start with q. Whatever q is, doesn't matter, as long as, is a number that's in the domain of log. So whatever that is, whatever we do here, we do to it with the log, we cancel it with the exponentiation with base 4, so they cancel each other. So what we end up on the left is q, and on the right is 4 to m. So this expression and this expression say exactly the same thing. This one says 4 to mth power equals to q. What does that say? 4 to mth power equals to q. Okay, what about this one? Well, that one we start with log base a of b equals to c. So we have to take a, which is the base, and raise it to what? Log base a of b, and also raise it to the power of right hand side. Now this right here is just b, and then equals to a to c. Again, this is exactly the same as this. This one says a to the power of c equals to b. This one says a to the power of c equals to b. Well, I said a to the power of c equals to b. Okay, the same thing. All right, so what about this one? Well, that one is basically the same setup. So let me do that one in this area right here. So we have log base 16 of y equals to x. So now we just take, I don't want to write it, I just write 16 to the left side, 16 to the right side. So the result of all that would be just y, and the result of this is 16 to x power, right? 16 is the base. But what about this one? Well, here the base is x, right? So I'm going to do x to the power of log base x of 64 equals to x to the power of y, right? X to left side, x to right side. Now, since the bases are the same, this cancels, so we get 64 equals to x to y, right? X to y power is 64. X to y power is 64. Okay, so let's do some more problem. Let's go to 26. So for the following, solve for x by converting the logarithmic equation to exponential. So let's see. So these are very simple equations. You can see. So this one right here, it says that log base 3 of x equals to 2. So to take care of this, we have to get rid of log. So again, we do 3 to this side and 3 to this side. Right? What do we get? Well, on the left, remember the bases here are the same. The base here 3, base here is 3. Cancel each other. So we get x equals to 3 to the second power, which is 9. Right? Now what about this one? Well, we do the same thing. We take 2, raise it to the left side, take 2 and raise it to the right side. So what do we get? Well, this part is going to give us just x. Why? Because the bases are the same, right? So they cancel. You start with x, do this to it, and then do this. They cancel each other, so you get x. And it's 2 to the negative 3. And we know 2 to negative 3 is 1 over 2 to the third power, which is 1 over what? 1 over 8. Okay, and what about this one? Well, this one, you have to do 5 to this side and 5 to that side. So again, you start with x, you do this to it, and then this, they cancel each other. So x equals to 5 to the second power, which is 25. Okay? That's the idea of this. Let's do a few more. What about 36? Well, here it says use the definition of common and natural logarithm to simplify. All right, so let's see. Now remember definition, we said what? The idea of, so let's do this one. So what is log of 100 to the 8th power? Now we know that when we write log base 2 of 8 equals to 3, it means what? 2, it means that 2 to the third power equals to 8, right? So if I don't give you the 3 here, you should know the answer is 3, because you know that 8 is what? 8 is 2 to the third power, and you know the answer is 3 because we can simplify it, right? These two cancel each other. So it's not that easy to find log base 2. It's not possible to find log base 2 of 7, for example, this way, right? Because how can we write 7 as a power of 2? Because it's not a round number. So we use a calculator for this question. But we know that we're looking for an exponent of 2, right? That if you raise it to that number that we don't know, we get 7. Well, we know that logarithm is an increasing function, right? This logarithm with the base greater than 1. So that means what? That means we know 2 to the second power, that's 4, and we know 2 to the third power is 8. So the number that we're looking for is between 2 and 3. So this number is going to be 2 point something. We don't know that decimal place. We don't know after the decimal, but we know it's 2 point something. Can't be 3 and can't be 2. Has to be somewhere in the middle. So we can do that. But what if we have something like this? We are supposed to do this without a calculator. So we have to simplify this. So this is the trick. If we have a base here, if we have the same base here and to some power, let's say a, then the answer is 8, right? we can simplify. So if we can write the argument of log as base to some power, we can easily simplify it. The same is true for what? Exponentiation. So if we have some base here, right? And then if you raise it to log base, the same base, and a, the answer would be a. Why? Because this is exponentiation and this is logarithm, they cancel each other, right? All right, so let's see if we can do this without a calculator. So what I need here is a power of 10. Why? Because the base is 10. So I can write 100 as 10 to the second power and then to the 8th power, right? Which is what? Which is log. Remember, we don't write the base here because we know this is common logarithm, and by convention we don't write the base. So that's not the base, that's the argument. This whole thing is the argument of log. That's what log applies to, right? It's an argument. Okay, so the argument would be 10 to 2 times 8 is 16. Remember, we multiply the exponents. Now, this answer is 16. Why? Because you see there is a 10 here. Let me write it for the last time. The bases are the same, so they cancel each other, right? So we get that. All right, can we do the second one like that? What about this one? Well, yes, because the base here is 10, right? Because it's not written. So since the bases are the same, the answer to this is 32, right? That's easy. So it's base, let me rewrite it here. So it's 10 to the power of log base 10 of 32, right? That's the argument. And the base here is 10. So these cancel each other. So we just get 32. Okay, what about this one right here, the last one? Well, this is 2 times the log of 0.0001. Now, we know that 0.0001 is actually what? Is 1 divided by 1 with 4 zeros, right? That's what this means, right? This is the 10th place, that's 1 over 10. This is 100th place. This is 1000th place. And this is 1 over 10,000th place, right? So that means 1 over 10,000, right? Okay, so now we still can do it using that structure I talked about, right? So if we have log of the same base here and the base here, then a, the answer is a. But this is not 10 to something. We're going to make it 10 to something. And we know how to do that because we can write this as 10 to the 4th power, right? 1 with 4 0 means 10 to the 4th power. And now we can write that as 10 to negative 4, because if we bring it up, it becomes negative. Now this is easy. It would be 2 times whatever this is, and this is negative 4. So the answer is negative 8, right? All right, so that's number 38. Let's do a few more of these. What about these right here? It says, for the following, evaluate the base b without using a calculator. Again, you have to do the same thing here, but with no calculator, right? So the first one is, again, log base 3 of 1 over 27. Or the trick we can use is this. It's not a trick actually, it's a rule, but so if we have the argument of log is the base to some power, the answer is easy, it's just that power, right? Because the question in the logarithm is base to what power is the argument? Well, the base to what power is the base to a? Well, a, right? So we can't do this here in this example because the way that is given is not a power of 3. But obviously you can make it power of 3, right? You can make this as 3 to the third power, then make it as 3 to negative 3, the argument. And now these two are the same, so this is negative 3. Now what about the next one? Log base. What about log base 6 of a square root of 6? Now does this look like that structure? No, but we can make it. What is the square root of 6? Well, we have a rule that says square root of a to nth power, like that, not square root, nth root. That's the same as a to m over n, either this way or this way. So radicals are nothing but fractional powers, right? So there is a 1 here and there is a 2 here we don't write. So this is really 6 to 1/2, which is 1/2. Again, because these cancel, right? All right, and is there another one we can do? Well, no, that's... Okay, so let's do a few more this section. What about number? It says here, for the following, evaluate the natural logarithm expression without using a calculator. Okay, now the expression is natural log. So let's do this. Let's get all three. Now, does this look like this is structured? Again, we talked about if you have the base here and the argument is also base to some power. Does it look like that? No. Well, or maybe yes. Well, if you know about ln, that ln is what? Ln of something is actually log base e of something, right? So this is really log base e, and looks like the argument has e and then 1/3. So the answer is 1/3, right? So remember ln and e cancel each other. If e is in the argument of ln, then they cancel each other. Okay, what about ln 1? Now, log of any base of 1 equals to what? 0. Remember the graphs? The graph of log with base greater than 1 looks like this, and the graph of base between 0 and 1 looks like this. All the members of these two families go through 1, right? And the y equals to 0 when x is 1. So that means logarithm of any base of 1 equals to 0. And this makes sense because logarithm says a to what power equals to 1. Well, any number that we use for logarithm here, any number to 0th power is 1. So 0 is the answer. So the answer to this would be 0 for any log. And what about this one? Well, this one says ln of e to negative 0.225 minus 3. Well, we know this right here, that cancels, so we just get negative 0.225 and then minus 3. Is it minus or yes? Minus 3. And that's just negative what? Negative 3.225. Right? All right, so without a calculator, we did this. And let's do a few more. So for the following, evaluate each expression using a calculator. Now, what about calculator? Well, the calculator has what? The calculator has log base 10, which is right there. See log base 10? And it has log base e, which is ln. So for example, what is log of 100? What is it? Did you say 2? Yes. And what is log of 1? Well, 0, right? So if we have base 10, we can use that. If we have base e, we can use that. So what is ln of, let's say, let's get e. E to the 5th power. What do you think the answer is going to be? Yes, 5, right? Because they cancel each other, so we get 5. So calculator has ln and log, so if we can't do it in our head, we're going to do it with what? We're going to do it with calculator. So what is 0.04? Well, we go to log 0.04. We clean that. So log 0.04 is negative 1.39 is an irrational number, so we can round to the 1000th place. We get, negative 1.398, right? And what is ln 15? So ln 15 is that number, and you can cut as many as decimal places as you like. What's ln 4 over 5? So it's ln 4 divided by 5 is that. What's log square root of 2? Well, is log and square root of 2. There. Okay, so that's how we use the calculator. Now, let me go do the next section, which is 6.4, and we're going to work with graphs of logarithmic functions. And I'm going to change my mind here. I'm going to do it in a different video, so I don't want to make the videos too long. So I'm going to come back and say again, bye and take care. I'll see you in the next video.